Let's see here. Let's draw the sphere first. So what if I cut out a hole of radius 1 meter? So this is, now the charge is distributed. Let's assume we could do this two ways. We could say we took a 10 nanocoulomb sphere and we took a piece of the sphere out, but that affected the charge of the sphere, you see. So in other words, we took a chunk of the sphere out and made a hole, and now we have a new charge. Remember, the charge of the sphere was 10 nanocoulomb. So if we're going to say that we took a piece of that sphere out, that means the charge is affected, right? But probably the more interesting way to do it is to take a chunk of the sphere out, and let's say the charge is affected, but now put some more charge on there so that the overall charge is still 10 nanocoulomb, you see. Now what's going to be the electrical field at the same location? So we can say, what's the electrical field at 2, 3, 4? What's the electrical field at, what's the flux at 2, 3, 4? The reason I want to keep the total charge the same is because then we can kind of compare the numbers more versus saying, oh, I took the chunk of that charge and now the charge is reduced. You see? Okay, so now what would it be? At 3 and 4, I expect no change, right? Once I'm here at the surface, the equation is kq over r squared, where q is the net charge. So I expect here and here not to be influenced by the hole. You see? Q at r equals to 3 is still going to be, what, 10? E at r equals to 4 is still going to be, what was it, 5.625. You see why? Because once I'm here, the net charge enclosed is the same, and once I'm here, the net charge enclosed is the same, because I'm keeping the total charge 10, no matter what hole I'm making. The only one that should be affected is the charge, the electrical field at the 2. So now if I do a Gaussian here, what's the charge enclosed within that space, right? So I could still make the same argument that the charge enclosed here divided by the total charge of the sphere is equal to the ratio of the volume of this guy to the volume of the whole thing, you see. Well, of course, I'm still assuming that the volume charge density is the same, the rho, the volume charge density throughout the sphere. So then Q is going to equal Q. What's the volume of a spherical shell? This is called a spherical shell. So what would be the charge enclosed there? That'll be, let's see, volume is 4/3 pi r cubed minus the inner radius cubed, right? The r of where I'm at minus the inner radius, basically the radius of the hole. Divided by, and then the volume of the outside, the volume of the whole thing is going to be what? 4/3 pi, the radius of the sphere minus the radius of the hole. You see? So you're doing basically the volume of this whole thing is 4/3 pi r cubed minus r1 cubed. R1 is the radius of the hole over 4/3 pi r cubed minus r1 cubed. So then cancel that. And then this is going to be 2 cubed minus 1 cubed over 3 cubed minus 1 cubed, right? And then that multiply that by the total charge of the sphere, 10 nanocoulombs. So that's going to tell me how much charge is included just in that.
Where are you getting those numbers from?
Oh, those are just numbers I made up. I said the hole happens to be a one meter hole I cut out. And then those are...
The radius is 1 meter, or?
The radius is 1 meter, yeah.
So it's 2 meter diameter.
Yeah. Yeah. And then the original sphere had a radius of 3 meters. We were already given that. And now I want to find the electrical field at 2 meters. So the question is asking, what is the electrical field at 2 meters? See where that numbers are coming? So this is the radius of the Gaussian surface where I'm at, minus the inner radius, the hole radius, and this is the sphere's radius. Okay, then I'm getting here 8 minus 1, 7 over 27 minus 1, 26 times 10 times 10 to the minus 9. Okay, so that's the enclosed charge, right? This is enclosed charge. So then what I'm going to do to find the electrical field, I'm going to do E times 4 pi r squared is charge enclosed over E0. Okay, so then E is going to be 1 over 4 pi E0 r squared, and then Q enclosed. And then I could turn this into a K again. K like that. So then I'm going to have here 9 times 10 to the 9th. Charge enclosed, this guy. Over, and then what's the R? That would be this R, right? The radius of where I'm at. So 2 squared. So for this one, I'm not necessarily driving a general equation. I could if I wanted to, but in this case, I don't have to. I can just find the...
Well, why'd you get rid of the 4 pi? How did you do that?
The 1 over 4 pi is 0. Whenever we see that, we can replace it with the Coulomb's constant K. Because Coulomb's constant is less rounded, so I'd rather use the less rounded one. 9 times 10 to the 9th is pretty exact. Okay, so now nine times 7 times 10 divided by 26 divided by 4. Ooh, 6.057 newtons per coulomb. Interesting. That's weaker than the electrical field for without the hole, huh? You see, by the time we reach the surface, they should be the same. You see, the electrical field should be the same as the regular one without the hole. So this one is weaker. Let's see, can we have a reason why? What's the hole doing? Oh, if I'm at 2 meters, the enclosed charge is less than it would have been if there was no hole. Yeah, that makes sense. So in other words, you're taking the same amount of charge, the overall charge, distributing them over this much area, this much volume, right? So then if I'm at 2 meters, there's less charge enclosed, so it takes a while for the electrical field to pick up pace. The other one was what? The electric field. I think it was 6.67. Where did I write that? Yeah, 6.67, I think. Yeah, 6.67. So this one was 6.057. So then what's going to happen to the flux then? The flux should also be less because it's the electrical field times 4 pi r squared. Right? So the flux should be less if the field is less. What was the other one? 335, yeah. In other words, it takes more time. It takes more time for the flux lines to start appearing, the electric field lines. But by the time we reach the surface, same number of lines will appear as the other one because the total charge is the same, you see. But it takes more of a while for it to get going. Any questions? I know maybe I'm going kind of fast, so please stop me, slow me down, ask question. So far so good, or what?
Yeah, so far so good.
Yeah? Okay, you guys are pretty good understanders. Usually there would be, when I'm in class, by this point, I see a whole lot of faces just frowning or lost. Okay, so 304. Oh, so the flux is less, the electrical field is less. So I think we answered everything there. Okay, how about if the hole is like this? Let's say it's a radius is 1 meter. So radius is 3 meters. Let's see. Let's say the hole is positioned. The radius of the hole was 1 meter, right? So it would be something like this. You see, so from here to here would be 1 meter, and then the radius of the hole is 1 meter, right? So then this would be the center of the hole. Okay, so let's again assume that the total charge of the sphere is such that it's still 10 nanocoulombs. But now there's a hole inside it has. So you see, you got the same amount of total charge here, but then it's got a hole here. So what's the electrical field as I go up this way? You know, let's say 2 meters would be right there, right? 2 meters. But here we could answer, okay, what's the electrical field here, here, and here? Kind of, those are the interesting points, you see, as we go up this way. How would we approach this one? Well, the electrical field at 3 should still be the same because that's at the surface, right? So that's still 10. Of course, the electrical field at 4 would still be the same because we're already outside. So you see, if I'm outside here, interestingly, it wouldn't matter. Let's see here. As long as it's Oh, you know what? At 4 it might affect. Oh, let's see. Okay, you know what? Okay, let's just say let's not make any biased statements, and let's say these might change also. Because the problem with this scenario is that the hole is not symmetric. For the other one, it was easy because the hole was centered right here, so everything was symmetric. Whereas this one, it's off-centered. Okay, for these kind of problems, we use the idea of superposition. So here's what we do. If we want to find the electric field at any point, then we're going to say, assume that this is comprised of two spheres, one a solid sphere without a hole, right? And then one hole. And now this hole has a negative charge, you see. So the hole behaves as a chunk that has negative charge in it. And then the electrical field created by this is the superposition of the electrical field created by a solid sphere and then a positive charge Q and a sphere of negative charge, little q. Do you see the idea? So the electrical field of this at any point is a superposition. That's the idea. So superposition principle. We kind of do this back in Physics 101 also. When we have something like this, and the problem tells you, find the center of mass of that shape. If you remember, Daniel, we might have done that in Physics 1, yeah? So we say the center of mass of this shape is the center of mass of this guy, which is at the center, minus the center of mass of this guy, but you treat this as a negative mass, as if it's a negative mass, and this guy with a positive mass. So the center of mass of this sphere is at its middle, but it's got negative mass. Then you do x center of mass is m1 x1 minus m2 x2 over m1 minus m2. This is m2 is considered like a negative mass. So you eat a piece of the apple, let's say, you know, and then where's the new center of mass? Well, the new center of mass will have shifted downward, you see, towards negative. So then it's going to be m1 x1 minus m2 x2. So you have to find the mass of this guy, and the center of mass is easy. It's right at the center. So the same idea of superposition now we're applying to electrical field, and this could also work for gravitational field. So now, first we have to find, if we know that the charge of this guy is 10 nanocoulombs, we would have to find what the charge of a complete sphere will be, because it will be more than 10, right? So what would that sphere's charge be if this is 10, do you see? You know what, we could probably find this charge more easier. What would this charge be? Because it's a simple ratio of the volume of this to the total volume, right? So we could say the little q times the 10 nanocoulombs, right, is equal to the volume of this thing times the radius was 1, right, over the volume of this guy. So the little q over 10 nanocoulombs is the ratio of the volume of this to the volume of that. So then this cancels this, so then that's going to be 1 over 27. So the little q is going to be 10 over 27 nanocoulombs. But of course, we're going to attach a negative to it because it's a hole. So now we attach a negative. So then what would the charge of this whole thing be? We could just add 10 to, we could add this number 10 over 27 to 10, right? Because then if we found that the charge of that would have been 10 over 27.
What are we looking for here? Like, what is like, what would the question be stated as?
Yeah, well, it'll say something like, what is the electrical field at 3 meters from the sphere? Like right there, basically. What is the electrical field at 3? And then what is the electrical field at 2?
Thank you.
Would be, at 2 would be right at the center of the hole. And then the electrical field at 1 would be right there. Yeah. Then you can also, once you find the electrical field, then you can find the flux. You see? So, yeah, I believe the charge of this will just be the sum of 10 to 10 over 27. Yeah. Okay, so then you just have 10 plus 10 27ths. That gives you what? 270, 280 over 27 nanocoulombs. Okay, so now let's say I want to find the electrical field here. Right at the edge here. What would I do? I would say take the electrical field that a sphere, a closed sphere makes right there. You see? So what is that equal to? So let's call that E1. You see? And then what is that? Well, I'm at the surface of the sphere, so I can simply use the equation for the surface of a sphere. K Q over its radius squared. You see that? So K is 9 times 10 to the 9th. Q is 280 over 27. And then nano cancels the 10 to the 9th. So I want to go slow and repeat everything so we don't go. This one's kind of a harder problem. So 9, this is the total charge over 27, and then the radius is 3 meters squared. Okay, so then that's the electrical field. 9 times 280 divided by 27 divided by 9. 10.37.
Wouldn't the 9s just cancel out?
Oh yeah, you're right. Yeah, yeah. I guess I could have done it. Yeah, you're right. This 280 over 27. That's still the same thing, right? Yep, you got it. Okay. So now this one. So now this guy creates an electrical field at its outer edge. Okay. So then that's going to add to this. Which direction? What's the direction of the electrical field created by this guy here? Well, since it's considered as a negative charge, so it's going to be down this way, right? Towards its center. Right? So then we'll call that E2. So what's E2 going to be? K Q over R squared. Right, so since I'm at the surface, I can just use the equation for the surface of a sphere. So then it'll be 9, and then the Q is going to be 10 over 27. And the fact that it's negative, I've already taken care of it by drawing it down. Over what's its radius? 1. Right? Okay. So then what is that? Everything goes 10 over 3. 3.33. Okay, so did I do that right? Okay, so 9, 10 over 3. Yeah, 3.333. So now, how are the two electric fields going to add up over there? So this is 3.333. And then the E1 was 10.37. So now you add those. One is going outward, the other one is going inward. You see? So the electrical field is 10.37 minus 3.333, 7.037. Okay, so E total is 7.037. Yeah, so it made it, because the hole is off center, it made the electrical field there weaker than it was. What was the answer when I was, even when the hole was at the center, what was the electrical field here at the edge? You see, it was still, I believe it was 10, right? The electrical field at the edge. Yeah, it still was 10. So making it off center is what's making it different. You see? How would you do the electrical field at this edge? I believe they're going to be different now. All the edges are going to be different. How would you do the electrical field at the bottom edge? It's now going this way, right? So then you would do the electrical field created by a sphere at the bottom, right? And then the electrical field created by this guy at that location at the bottom. You see? So what would be the electrical field E2? Well, let's just call it E1 again. At the bottom would be what? Still the same answer. What was that? 10.37. Right? But what would be the electrical field created by this charge, which is located here? What would be the electric field there? Well, it'll be towards it because it's a negative charge. And what would its value be? What would E2 be? E2, and it'll be 9 times 10 over 27. So then what's the distance between the center of that and that distance? You see what I'm saying? So you're superimposing the electrical field that this creates at any point to the electrical field that this creates at that point. You see? So then this one creates, what would that be? What's the distance from the center to the edge? So then that's 1 meter. Another one, that's 2 plus 3, that's 5 meters. Do you see how I got 5? So here's the center. From here to here is 2, and then here to here is 3. So 5 squared. So you get what here? 10. 10 divided by 3 divided by 25. Ooh, very small. So then I subtract 10.37 minus 0.133. 0.37 minus 0.133. Oh, 10.2367. Well, now it's greater than the electrical field at the surface of the at the surface of the sphere with the hole, with the centered hole. See, now it's larger than that. So it's over here, it's really big. I mean, not that much bigger, but the other one was 10, so slightly bigger. But then here, it's smaller, you see. Yeah, it kind of makes sense because you have a chunk of hole there, so less strength of the electrical field there. Yeah, it makes sense. So you could do kind of weird points, but it gets harder, of course. If I wanted to find the electrical field here, what would it be? The sphere makes an electric field this way. The hole makes an electric field towards it this way. Oh, you see that? So then it ends up being electric field is off-centered like this. So it almost looks like the electrical field here is going to be like this. Like this. So it's going to be like this. Electric field is going to be like this. It's not going to be coming out radially. Here it's good radial. Here it's radial. Like this maybe. You see, they're skewed. They're skewed. But those points are harder to find because there's an angle there. So we won't do those. Okay, what would be the electrical field right at the center of the hole? Okay, so that would be at 2 meters, right? So at 2 meters, so then at the center of the hole, so then again you do the positive charge. So then you say, what's the electrical field at 2 meters? So what would that be? E is KQ over R cubed R, right? So 9 times 10 to the 9th, 10 nanocoulombs over 3 cubed times 2 meters, right? Oh, no, we can't use 10 nanocoulombs. Remember the solid sphere, we got 280 over 27. 280 over 27. That's it, yeah. So this one cancels that. So I'm using the 280 over 27. Two 280. Oh, let's see. 280 times 9 times 2 divided by 27 divided by another 27, 3 cubed. 6.913 newtons per Coulomb. Right? Then we're going to subtract from there the electrical field created by the negative Q at its center. You see? What is that? What is the electrical field created at the center of a insulating sphere? So we'll say this is E1. Anyone? Daniel?
Figured it was 0, yeah.
Yeah, exactly. When something is 0, you feel like you're thinking wrong, right? It's too easy.
Yeah, it's usually how it is.
Yeah, you're afraid to say it. Yeah, exactly. So the field at the center of that negative Q would be 0. So this is the total electrical field. So over here, the electrical field was, what was it? 7.07 at the edge, 7.037. Wow. But over here is almost that. It's 6.913. It's really weird how that works. Because as you're going out, see, as you're going to the center, the hole doesn't do anything. So imagine this is you kind of analyze it this way. You're going out this way. Then what's happening as you're going through the hole, you know? Try to think of that. What are these charges doing? You see? So once we find out what the electrical field here as the bottom edge, we can kind of start guessing. Actually, in this problem, there's actually going to be an electrical field at the hole too, right? Oh yeah, the electrical field will be 0 somewhere here, I think. Then when you go here, there's actually gonna be an electric field, right? You know why? Because if you do the superposition theory, the solid makes no hole at the center, but this negative Q makes an electrical field towards it, that way. So starting somewhere here, let's say, the electrical field is 0. You see, where the field of the solid and the other one cancels. So electrical field is 0. Then it starts to increase. Then when you get here, it increases. And then from here to here, it doesn't increase a lot, but it does increase slightly from 6.9 to 7, you see. So then what would be the electrical field at the bottom at R equals 1? So then what would that, electrical field total at 1. So then you're going to do the electrical field at 1 from or this. So it's just going to be 9 times 280 over 27 over 3 cubed times 1. So the solid one is just simply going like a linear function, right? So it's half of this. 6.913 divided by 2. Remember that we could use that linearity to our advantage. For a uniform charge density, it's linear. So at 1, it's half of 2, and 3 is 3 times bigger than 1, you know. So it's, so then it's just going to be 3.4565. But then what's going to be the electrical field of the negative charge there? The negative charge is going to create an electrical field towards it, you see? So on this side, the electrical field it creates is this way. On this side, the electrical field it creates is that way. So if I'm on the bottom portion of that, the E2 is up, you see? So then what is E2? Well, it's the same thing that we got for the E2 from the top, but it's just the direction is opposite. You see, since we're treating this like a negative charge, the E2 is towards the centers instead of being away. So what was the E2 that we got? Was it 3.33? 9 times 10 over 27. Yeah, I think here it is. 9 times 10 over 27, 1 squared. That's the electrical field at the surface of the negative charge, 3.33. There you have it. So then the E2, but the E2 is that way, you see. So E2 is 3.333. So then I add that to the electrical field created by the solid one, right? 3.333. 6 point, let's see here, 8, 9, 7. Oh, wow, that's crazy. 6.798. So the electric field right there is 6.798. The electric field right there is 6.913. And the electric field there was 7.3037. Now we can find out. Remember earlier I was saying, oh, once we're outside, we don't have to worry about where the hole is and stuff. Well, am I right? Maybe I'm not right. So how would we answer that? Let's say I'm at R equal to 4 meter. If I was right that we don't have to worry about it, what should the electrical field come out at R equal to 4? At R equal to 4, well, then it should just come out KQ over 4 squared, right? If I could use that fact that once I'm outside, I don't care about where the hole is, right? What did that give us when we did the 4 meter? 5.625, right? 5.625. What's your gut instinct? Now that we do it with the superposition method, are we gonna get 5.625? Or are we gonna get that, no, this doesn't work anymore? I feel like it's not gonna work anymore because when you're 4 meters this way, it's also not gonna be, it's gonna be different when you do the superposition, right? So I feel like it's not gonna work. So how would we do it with the superposition? We would do the electrical field of the solid one. E1 would be what? 9 times 280 over 27 divided by 4 squared. So I'm just doing KQ over the distance squared, right, for 4 meter. Hmm, 5.83333. That's weird. Might 9 times 280 over 27, 4 squared. Yeah. Let's double check that, make sure. 9 times 2. Yeah, okay, now how would you do the electric field of the negative charge? Then it'll be the KQ, negative KQ over R squared, right? Because the negative would create the negative charge would create an electric field towards it, right? Negative 9, what's the charge of it? 10 over 27ths. And what's the distance from the center of that, right, to the 4 meter mark? So from here to here is 3 meters. From here to here is 1 more meter. So that's 4 meters. From the center of that to there is what? 2 meters, right? Am I right? Yeah, so 3 and 4, that's would be 1 meter here. Yeah, 1 meter, 1 meter, 2 meters. So it'll be negative 9 times the Q over the 2 squared. Divided by 27 divided by 4. Negative 8 Negative 0.8333. Oh, then you add these, superimpose them, right? Well, that's just going to give you perfectly 5. So is that what we got when there is a hole or when there's no hole, right? The 5.625. No, it's slightly smaller. So on the side of the hole, on the side where the hole is, we're getting slightly smaller electrical field than would have been
I mean, we could probably attribute that to being to there being less area, right? Surface area on the sphere, technically.
the total surface area on the total sphere. No, well, no, because the hole is inside of it. It's like an apple with a chunk taken out from the inside.
Right. Because I
I think that affects the surface area of the sphere.
Right. Because I was just thinking, like, from Gauss as well. Like, if we're thinking about Q enclosed, we still have the same Q enclosed, right? Like in total, so we would have a 10 nanocoulombs with even with the hole.
Yeah, but the distribution of the charge is that it kind of shoots off to the side, the charges. So what we're seeing is that the electrical field here is quite weak compared to what it was when there was no hole.
Right.
On the other side, it is a bit stronger. So I'm going to say that the electrical field here is weaker than what it used to be. Here it's a bit stronger than what it used to be. And then everywhere else it's a bit curved like that, but it might be stronger than what it used to be. And then when you get to the here, by the time you get to there, it gets weaker and weaker.
Right.
Something like that, probably visually.
Yeah.
Now, when you get to the 4 meter mark, same thing probably happens. Here, it's a bit weaker than when the hole was not there, you know. But how about flux, though? How about flux at R equal to 4 and at R equal to 3? Well, flux is just going to be Q enclosed over E0. It's not really going to care. Remember, flux is a scalar, whereas electrical field is a vector. So flux is not going to care about the direction of the electrical field. It's just going to take the E field and dot it into the area. Then it's just going to take the sum of it. And then it's just going to say, well, the flux, no matter what the direction of the E, it just should equal to Q enclosed over E0. So the total flux, once I'm at the surface, should not change. So it should still be equal to 1130. And at R equal to 3, it should also be 1130. Was it 1130 once we went outside? It's that value that, yeah, 1130, right? This one. So it doesn't matter if the hole is off center, this number doesn't change. The flux doesn't change. Flux doesn't care about the distribution of the hole, where the hole is, just cares about where the charge, how much charge is inside. And it doesn't care if the charge is centered or not. Remember yesterday's problem? I was saying I can do the charge off center from the inside the cylinder and they still be the same flux. It's kind of hard to believe that electric field will be affected, but not flux, right? But that's the truth.
Right.
So even though the electrical field here is smaller, a bunch of them are also bigger, slightly bigger. So when you do the integral, it will work out. Now, if the flux at 4 is easy to do, the flux at 3 is easy to do. Okay, but if the problem asks the flux at 2 meters, ooh, that's a nasty problem. You have to try to figure out how much charge is included in a radius of 2. I guess it's not that bad. Oh, actually, it's not that bad. Just when I was saying it's bad, you take the volume of this and then take this chunk out. Then that'll give you the flux at 2 meters. Oh no, but this is nasty, huh? How do you take this portion out? What would be the volume of that? We have to take that volume and subtract it from the volume of the 2 meters. That's some calculus problem, huh? Well, it's probably doable, but I don't know if it's worth going there. Yeah, it's probably doable. Some integration that we would have to do to find this volume. And then once we find this, we take that out of this volume. Then that will give us the charge enclosed over E0. And that's it. For flux, that's all we have to worry about. Just calculating the volume. So if I want to know the volume, if I want to know the flux at 1 meter, oh, then that's the same as if there was no hole. You see? Well, actually, no, because the charge is different. The charge is different, yeah. In other words, what you have to do once you're inside the sphere, it's tricky. The charge enclosed is going to be over E0, is going to be the total charge times the volume V prime over V, right? V is going to be the volume of this, right? Which I think we got an answer for that, didn't we? Yeah, I think somewhere we got an answer for that. So that's V. So then depending on where they ask for the flux, if they ask for the 1 meter, you get the volume of that. That's easy if they ask 1 meter. Then you get the volume of that. Then you divide it by the volume of this whole thing. Let's see. That gives you the flux there. But if they ask at 2 meters, then you go like that. And then you take this chunk out of there. And you get the volume of that piece. You see? And then you put that here. But this stays the same. You see? The total V stays the same. So for flux, you're not really utilizing the superposition concept that we talked about. You see? You're just saying, what's the total charge enclosed? And you're just worrying about the ratio of the volumes. Okay?